Hi, I am Vanessa Steindorf. Today I'm going to talk about a model applied to a multi-serotype infectious disease. So, dengue fever is a multi-serotype infectious disease. It's caused by dengue virus, is endemic in subtropical countries, and that is transmitted by infected mosquitoes. So some features of dengue fever spread continues to pose challenging mathematical modeling, and we proposed integral differential equation system, a model, to study the disease, the transmission of dengue fever. So we applied for this this model to understand dengue fever. Our main goal is to include and analyze the effect of a general time delay that is describing the cross-immunity protection between the serotypes, and also to analyze the effect of antibody-dependent enhancement. Both are characteristics of dengue fever. So what is cross-immunity protection? Is when the infection with one serotype leads to a short-term protection for the other 3 serotypes. In dengue fever, we have 4 serotypes. And antibody-dependent enhancement was proposed to explain the occurrence of dengue hemorrhagic fever in secondary infections when the individual gets, after the cross-immunity protection, he became susceptible for the other 3 again. And after he is infected for the second serotype, there is a occurrence of dengue hemorrhagic fever, so antibody-dependent enhancement was proposed to explain that. So we are going to represent the antibody-dependent enhancement through a constant phi, assuming that briefly exposure to one serotype for dengue fever results in increasing of the susceptibility for reinfection. And we're going to represent the cross-immunity protection between serotypes, assuming a function, a general function per immunity period. So PI would be the function that describes this immunity period, the time that an individual remains in the cross-immunity class. So here you can find a flow chart, a diagram between the interactions between the classes. So we divide the population in classes, as described. The susceptible class, I1 and I2 infected for one serotype and the second serotype. Here, for purpose, we just put 2 serotypes. Okay, so after infected, the individuals goes to the cross immunity class, and he spends some time there. After there, he recovered for the first one serotype, and then became susceptible for the other one. And here he became infected again for a second serotype. And then we are assuming that after these 2 serotypes, he recovers for all of it. He cannot become susceptible again. Here is the model for 2 serotypes. Here you can see that these terms describes the general period for being a cross-immunity class. So after he's infected for one serotype, he moves to the cross-immunity class, and here describes the time spent on the immunity, the cross-immunity class. And then he recovers and became susceptible again. To study this model with general period, with this distributed delay term, we use the ideas in Brouwer. So we analyze a limiting system that is a perturbation of this this model. So then we are going to study this limited system. So this is the theorem that we use to analyze the stability of the equilibrium of the limiting system, and then we conclude we can find, assuming some hypothesis for the general function P, assuming this hypothesis for this general function, we could show the stability also for the system that we proposed. So now I'm going to talk about our results about the equilibrium, mathematical result about the equilibrium and the stability of the system. So we find the trivial equilibrium that will be represented for there is no disease on the population. Then we also show there is two binary equilibriums. That is when we have just one serotype or another serotype. And to be in the invariant positive region, it has to satisfy some conditions. This condition here, beta 1, that is the rate for infected rate over the time spent on the infection class. So if this number is greater than 1, then we have a boundary equilibrium for one strain. And if this number is greater than 1, then we have the other equilibrium. Of course, we're going to define mathematically these two numbers as the basic reproduction number for the system. So after that, we can assume that one strain is stronger than the other. So if this condition is satisfied and this one, then we could show that we have a other equilibrium in the interior of invariant positive region for the system. We call it coexistence equilibrium. So in this case, if this condition is satisfied, then we have a coexistent equilibrium in the interior or invariant positive region. This threshold here, this condition, this threshold, it's an important threshold in models with multi-strains. It is called invasion reproduction number, and I'm going to talk about a bit later. So the positive equilibrium must satisfy some conditions, of course. I'm going to tell you about the basic reproduction number. So we define mathematically the basic reproduction number for each strain. So the maximum of these two will be the basic reproduction number for the model. So these thresholds, the basic reproduction number and invasion reproduction number, is going to define the stability of this equilibrium. So when the basic reproduction number is less than 1, then this is free equilibrium. when we don't have disease, is stable, and is unstable if it's greater than 1. So about the invasion reproduction number, this threshold is going to define when the coexistent equilibrium will be in the invariant region, and also about the stability of the boundary equilibrium. So one of the boundary equilibrium will be always unstable, while the invasion reproduction number is going to define where the other boundary equilibrium will be stable or not. So if the invasion reproduction number is less than 1, then it will be stable, and if it's this is bigger than 1, then it will be unstable. Of course, this invasion reproduction number is a very important threshold, as I was saying. So because biologically speaking, there is a range for values of the infection rates for which strain 1 cannot invade the population if the strain 2 is endemic. Yeah, so this is results for local stability. Also, we have other results, mathematical results about this model. So we show the global stability for the disease-free equilibrium using Lyapunov functions. Sorry. So this is the small summary for our mathematical results when we have equilibrium or not, when they are unstable or unstable, locally stable or globally stable. This is a summary of our mathematical results. We also have results about the stability of the coexistence equilibrium. Okay, so we show through numerical experiments when the coexistent equilibrium is stable or not. For that, we use the parameter phi, that is the parameter that represents the antibody-dependent enhancement. So we use this parameter to study the stability of the coexistence equilibrium. And for our numerical experiments, we use values from MASAD study. So MASAD study dengue fever, and we have these values for the parameters, and also MIDA and Ferguson. Yeah. So here we have a small video showing that it's not showing. Sorry. Here. Now it's showing that when the parameter phi is varying, right? In green here we have the values for the when the boundary equilibrium is stable, right? So this green line here is when the invasion reproduction number is equal to 1. When it is equal to 1, that in green area here, we have the values where the boundary equilibrium is stable. So when phi is varying, this region is going to be smaller when the boundary equilibrium is stable. So in this pink area here is when the coexistence equilibrium appears in the invariant region. So as phi is growing, as phi is increasing, we have that, in fact, the coexistence equilibrium is in the invariant region. So to show, we also would like to know about the stability of the coexistence equilibrium when using invariant positive region. So here we do numeric experiments to show that the eigenvalues of the coexistence equilibrium in the complex plane. And this figure here shows that a purely imaginary eigenvalue appears, showing that we have a Hope bifurcation for this parameter. So the coexistence equilibrium is stable until this this value phi, this critical value, right? And then we have a bifurcation, a Hope bifurcation, and this is the bifurcation diagram for when the phi varies. We have then the conclusion. So our result is it's a mathematical result. So these models that we can study that carry these mechanisms like antibody-dependent enhancement, mood strings, and the cross-immunity protection. They are very important because we can show that a coexistence equilibrium is possible. So the thresholds that we show, like the invasion reproduction number, is very important because it can determine whether the one strain can invade the other. We also show supercritical Hope bifurcation. So the parameter phi is very important because we could show that for critical value there is periodic solutions. We also could show that bifurcation stability does not occur in the symmetric manifold. So our results is mathematical results, but we can show also that we could give a lot of scenarios for dengue fever, and of course other kinds of bifurcations will be analysis would be necessary, because the factor phi, the parameter phi that describes antibody-dependent enhancement, this parameter is still unknown. So we could give only some scenarios showing periodic solutions and coexistence of strains. And yeah, this model, the main goal is to understand this dynamic of dengue fever using antibody-dependent enhancement, using coexistence of the using cross protection, right? So understand the dynamic of the disease at population level, and we try to explain why it's so hard to predict dengue fever because of these characteristics of dengue, such as antibody-dependent enhancement and cross protection. Yeah, we have work and challenge, and still we have to analyze other bifurcation structure. We also want to generalize for more than 2 serotypes. That's it. If you have questions.